In 2020, a group of researchers stumbled upon something that felt like a cheat code for intelligence. They found that if you make a neural network bigger, give it more data, and throw more computing power at it, its performance doesn't just get better, it gets better with the predictable smoothness of a physical law, like gravity. You could plot its expected ability on a simple log-log graph before you even started training. This discovery, known as a scaling law, suggested a simple, almost brutish path forward. If you want a smarter AI, just build a bigger one. The universe, it seemed, was rewarding sheer, unadulterated scale. But what is bigger in this context? It comes down to parameters. A parameter in a neural network is essentially a tunable knob, a single connection weight between artificial neurons. Think of it as one synapse in a vast digital brain. A model with a few million parameters can learn to distinguish cats from dogs. But a model with hundreds of billions of parameters can learn the subtle relationships between words, the structure of grammar, and the nuances of human intent. Each parameter adds a tiny bit more capacity to the model's understanding of the world, allowing it to form a higher resolution picture of reality from the data it's fed. Tuning billions of these knobs requires an almost incomprehensible amount of computation. Training a large model is measured in petaflop days, where one petaflop is 1,000 trillion calculations per second. The training run for a model like GPT-3 consumed energy equivalent to what hundreds of US homes use in an entire year. To keep these massive processors from melting, data centers require colossal cooling systems, sometimes diverting entire rivers or building their own power stations. The cost isn't just financial, it's a significant expenditure of global energy resources, all to adjust connections in a machine that is, fundamentally, just learning to predict the next word in a sentence. For a while, the immense cost seemed worth it because something strange was happening. Models weren't just getting better at what they were trained on, they were spontaneously developing skills they were never taught. This phenomenon is called emergent abilities. A model might be terrible at two-digit addition, but after crossing a certain size threshold, it suddenly becomes proficient at three-digit, four-digit, and even five-digit math. It could translate between languages it had barely seen during training. These abilities appeared unpredictably, like a phase transition from water to ice. This discovery was profound. It meant that scale wasn't just making models more powerful, it was making them fundamentally different, unlocking latent potential in the data. The race for scale, fueled by the promise of emergence, quickly ran into its first wall: data. There is only so much high-quality text, code, and imagery on the entire internet. We are rapidly approaching the point where we will have trained models on nearly every publicly available book, article, and website ever created. The next logical step seems to be feeding models data generated by other models. But this creates a dangerous loop. It's like making photocopies of photocopies. Errors and artifacts accumulate, and eventually the models could start training on a distorted, simplified version of reality, a process known as model collapse. Just as the "bigger is always better" mantra reached its peak, a new scaling law emerged. Researchers at DeepMind trained a model called Chinchilla. It was significantly smaller than its contemporaries, about 1/3 the size of GPT-3. Yet it outperformed them. The secret was that it was trained on 4 times as much data. This revealed a critical flaw in the original thinking. Previous models were compute suboptimal. They were too big for the amount of data they were trained on. The key wasn't just maximizing parameters, but finding the optimal balance between model size and the amount of training data for a given computational budget. This search for optimization is happening because we are hitting fundamental physical limits. Moore's law, the observation that the number of transistors on a chip doubles every 2 years, is sputtering out. We are approaching the scale where transistors are only a few atoms wide, and quantum effects start to interfere with their operation. The energy demands are also unsustainable. You can't simply double the size of your data center indefinitely. The quest for bigger models is no longer just a software and data challenge. It's a battle against thermodynamics and the atomic limits of matter itself. So, if we can't just keep getting bigger, what's next? The future of AI research is shifting from brute force to finesse. Instead of just adding more layers to networks, researchers are designing more efficient architectures that can learn more with less data and compute. They're exploring ways to make models that can continuously learn without having to be retrained from scratch. The path forward may not be a single monolithic model that knows everything, but a society of smaller, specialized models working together, much like experts in human society. The question is changing from how big can we make it to how smart can we build it.
Monotony has grown fast. Nearly 2,700 people have watched in the last few weeks, yet less than 0.03% are subscribed. It would mean a lot if you joined by hitting subscribe. And again, thanks for watching.